Ok, então, bom dia a todos. Vamos começar. So, good morning to all. Now we are going to discuss geometrical transformations today and how ROS supports them. So we are in part 11, and the first thing that you should do, this is very important to understand what happens in this class, is to see this theoretical explanation, not this one. Okay. So this theoretical explanation will tell you how ROS works with geometrical transformations, and the way it does this, it solves the problem is in a very smart way, because it brings the philosophy of doing the distributed systems. So the processing of the geometrical transformations is distributed in the sense that some nodes, some ROS nodes, can publish to the system the value of a particular transformation, while some others publish the values of other transformations. So you end up with a transformation tree that is something like this, where you have inside each circle, you have a coordinate frame. Then you have a topology between coordinate frames. So every edge between two nodes, between two circles, will be a transformation between two coordinate frames, okay? And these transformations between coordinate frames can be published either by a single node, all of them, or they can be published in a distributed fashion. And ROS can handle all of this. So I will not explain anymore, because you have to see the video. I mean, it's 30 minutes long, and I will take 30 minutes to explain once again. So I think it's more useful if you take a look at the video, and then if you have some questions, let me know. I know that you watched the video, right? So do you have any questions? Okay, great. Okay, I'm not sure if you did, but if you didn't, you should, for the rest of you. So we get started in exercise number 1, and in this case, well, not one is for the tutorials of TFs, and then we get started on exercise number 2. So what we want here is to create a node called circular frame, which will be able to receive the name of the parent frame and the name of the child frame, and then publish the transformation between both in such a way that the child is moving in circles around the parent. Okay, so let's get started with a typical ROS node, and then we start thinking about the specific issue. So here in part 11, I'm creating a new package called PSR 22T part 11 exercise 1. I'm going to make it depend on ROS CPP, ROS Pi, standard messages, and also TF, because I know I'm going to use the TF package. So let me go here. Now I have to search for some example of, well, I don't need to. Okay, so here we go. Inside the source, we need to create a file. Circular frame, which was supposed to be called circular frame.py. And so how do we get started? Well, this node will have to publish information in the form of geometrical transformations. So you have to take a look at the tutorials of TF, which you should have done in the first exercise. And you have here several tutorials. The one that interests us right now is ATF broadcast, okay? So to broadcast is to publish. And in this case, we have a code which I'm going to copy and then analyze a posteriori. So first, let me copy paste all this code, and then we adjust. Oops. Copy, paste. This is Python 3 for me. Okay. And well, this is a convoluted example. Let me show you what we have here. So starting from the main, we are going to initialize the node, and our node is going to be called the circular frame. Okay. Then we get a parameter, which for now we don't need, so let me just comment. And then we create a subscriber. We don't need subscribers here, so I'm going to take it away. When we had received a message from the subscriber, it was inside this callback that we would publish a transformation. So I'm going to copy paste to cut the code from inside the function inside here. Okay. So now look what's happening. There's something missing here on the bottom. If name equals main, is it like, huh? Ah, right. Yeah, I know, but I do it in another way. I do it like this. That's why I was getting confused. It's like this, right? Def main. Yeah, right. Okay, now yes, now I know what I'm seeing. So the first thing we need to create is what they call a broadcaster, which is a publisher of specific messages, which are the transformation messages. I'm just going to call it broadcaster. Then, having initialized such an object, we can use it to publish new transformations. So in this case, what we are doing here is we are defining a new transformation T, which is a transformed stamp. And you can take a look at this ROS message. So we can go to ROS TF stamped. ROS message, perhaps, message. Yeah, so here it is, a transformation stamp. You can see what it contains inside. So it contains a header, then a child frame ID, and then the transformation itself. Okay. The parent frame ID is here inside the header. So this frame ID is the parent. Okay. So this is what is contained inside a transformation message. A geometry message is TF. And we just have to fill in all the fields. So the stamp, we are going to put it with the time now. The frame ID, we are going to put it as the world. Let's call it world for now. Then the child frame ID, we can say, well, actually, let me call this one parent and this one child. Then we are going to put here some translation. Let's say 10:5. And then we have to convert some particular angle. Let's say 30 degrees. Times math.y over 180, just to write in degrees and convert to radians. And from the quaternion, which is this Q, we fill in the transform rotation. Okay, and finally we send the transformation. Okay, so this is what the node is doing, is just sending the transformation. I'm going to be sending it continuously, not just once, but all the time. So while true, or even better, there is something called ROS OK. Okay. I always forget how to write this. Okay. We did it before. I have to search. While ROS OK. Diga? Ah, it's shut down, I say. Is shut down. Here, right. Thanks. See. Okay, so now this is what we are looking for, and then we have here the rate, and we can sleep to get, in this case, 10 Hertz. Okay, so all this is inside the while loop. That's it. And so what will happen now is that when I launch this node, we will be continuously publishing a transformation and let's see how it goes. So first I'm going to launch here. Yeah, better, I'm not going to use this here, better here. So first thing that I will do is call raw score. Second thing is RVs. And finally, the third thing will be our own node. Where is RVs? Next to RVs, apaguei também. Okay, always on top. And now, finally, we get to launch our node. Our node is on package PSR 22T part 11 exercise 1. So cross run PSR 22T part 11 exercise 1. And it's not working because I think I need to give it permissions. So right now it's not green. That means it needs to be changed to executable permissions. Now it's green, it's okay. So now it should expand. Okay, so if we launch this, we will see nothing for now, yeah. Now, first we need to tell RVs to be, to draw the things in a particular reference frame. In this case, let's use the parent. And finally, all these things are not important right now. We are not using any of them. What we want to see is the display type called TF. So TF, here it is, okay? So this TF, what it will do is it will show all the transformations in the system currently, and we can do it with a bigger scale, for example, 4. Okay, and if you change the name here, not the name, the background color, for example, to black, you can read the names in white. Okay, so this is the parent, this is the child, and we are now publishing this transformation periodically. RVs is being able to show this because there is a message passing through ROS, so ROS topic echo, list. You can see this TF topic. So this TF topic is where our node is publishing information. So these are the transformation messages that we are sending with a particular X10 and the Y5 for the parent to child transformation, okay? So what we need to do now is to change the coordinates as a function of some angle. So we can have here an angle, let's call it theta, which starts from 0 and then increments. So theta plus equal 0.1. I'm not sure if this is too much or too little. If I don't think I even need to worry about this because the trigonometry functions don't have a problem if I, well, in any case, let me saturate here. If theta is bigger than math.pi 2 times, theta will go back to 0, okay? Now, this transformation, this angle will always be the same. And now what I need to do is to derive the X and Y value as a function of the theta. So let's define a radius. Let's say it's 5 or something like 3. And now we use polar coordinates to compute the value of X.
So in line 71, we set to as fast as possible the whether we initiate which are about non-static.
I think if only if it is static, you need to say it's static. If you don't say anything, that it's dynamic.
The difference is that the static are publishes once.
Yes, and more than that, it publishes on a different topic. Cross topic list. It publishes on TF underscore static. Okay. So in this case, the first version, so what I've shown until now, it was indeed static because I was not changing. It was always 10 on X, 5 on Y. But it was a non-static transformation that didn't change. Now we are going to change it, okay? So radius times cosine, I think it's math.cosine of theta. And here will be radius times math.sin of theta.
It didn't change, would it be more correct to publish it in the static?
Yeah, but if it's you save resources because when a node receives a transformation from in the static topic, it will know that it received this one and doesn't need to look for new transformations because it's always going to be the same. Whereas if you always publish the same message here with the same values, the node will be constantly updating for the same value, so you lose resources, but it's not so much. So it's in the end, it's almost nothing. All right, let's try to see if we can see some movement now. So let's run our node again. Okay, so here it is, it moves, it's alive. What can we do now? We can parameterize this in order to be able to change the parent reference frame's name, the child reference frame's name, the radius, the speed, and many other parameters. So let's just, I'm already thinking about the second exercise, so I should have tell you about the third exercise. So in this case, we are going to try to replicate the solar system, and we are going to do only the planets until Jupiter or Mars, I think. And the idea is that we are going to have several planets rotating around the sun. And we are going to need to launch for each of these planets a specially configured how is it called? Circular frame.py node. Okay, so we're going to call this one many times, one for each planet. But for that to work, we need to make it configurable. Okay, so let's make it configurable. What we need to configure? Well, first we need to configure the parent and the child frame, which is this one, right? So we need to somehow be able to change this parent and child. We can actually here do how's it? Ross names remap. Ross name remap. I forgot. I forgot. I never remember anything. Not here. In Python. Ross.py. Remap. Remap a host name. I think that's it. So is it Ross.py? I don't know. I have to search here my stuff, what I did. So 11, exercise 2, source. So Ross.py.remap name, that's it, okay. So better than searching for a long time. So, okay, so when I write here parent, I would like to be able to remap it. So I'm going to do Ross.py remap name of parent. And the same for the child. If I do here Ross.py.remap name of the child. So if I run this without nothing, that's okay. If I run this, remapping the parent to other frame, we should be able to see something moving. Right. Of course, we need to change to other frame. Yeah, now it's moving. Okay. So we are able to remap already both the child and the parent. Let me go back to putting the parent as nothing. Okay. Parent. And what do we need to do to change more? We need to change the value of the radius. So we can create here a parameter called radius, which will be an internal parameter. So pushed into the node's namespace. That's why you have the tilde, and that's going to be called radius. And here we can do the speed, perhaps. I'm not sure how we can do the speed. Okay. Yeah, we can actually, the speed is here, is how much you increment the angle at each iteration. So let's just do here the speed. You remember that if we don't give any parameter, we should have a default value, which is going to be 3 for radius and 0.1 for speed. Okay. And here we were already using the speed and the radius here. Okay, so I think that's it. No, that's not it. We need to take it away from here. Now I think that's it. Let's try. Okay, so now we have the child rotating about the parent. And if we say that the speed is going to be 0.9, it should move faster, right? Okay, so a reminder, when you want to change from the command line an internal parameter, you use the underscore, the name of the parameter. Okay, so it was underscore speed. I think that's it. What else do we need? I think we are changing just about everything we need.
So you need to also change the child's name.
Yeah, it's here, look. Yeah, it's here, look. So on line 27, I'm doing ROSPy remap name child. Okay, that one is done. Bruno, you were calling me? É que os parâmetros podem estar guardados, por exemplo, carregados num fecheiro ou coisa do género. Remapear um nome não é bem a mesma coisa que remapear que mudar o valor de um parâmetro, ok? O parâmetro é um parâmetro com um nome que tem um valor. E um nome é um nome para uma coisa, por exemplo, um tópico que você pode mudar. Veja outra vez a aula dos parâmetros, talvez. Okay, so I'm not sure if something else is missing, but if it is, then we come back and change it. Or we can instead look at here, but I don't think so. Yeah, radius speed, yeah, that's it. Okay. Now, we jump right away into exercise 3. So we are going to try to replicate the solar system. And we have here a table with the distances from the planets to the sun. And what we are going to need is to pick this up and launch several circular frames.py specially configured. So if we are going to launch a set of scripts, not just one single script, but many, we have to do a launch file. It's very helpful to have a launch file. So let me search for a launch file example. We spoke about launch files already, but I don't know where. Well, find launch. Come on. Here, not this one. This is to search content. To search is like this, launch. So gazebo, spawn, IMCL, bring up perhaps this one. Let's see. Okay, I'm going to copy and then work on it. So on part 11, which is where we are, our package will have a new folder called launch. On this launch, we need to create a bring up dot launch. I'm doing this on the exercise 1 ROS package. I'm not going to create a new exercise 2 ROS package. This is just to, not this one, sorry. Just to make it easier. Okay, VRE, Epsilon. Here's my launch again. Here. Okay. Lost. Wait. São as soluções, não quero soluções para nada. E agora aqui na parte 11. Bring up dot launch. Yeah, okay. Right. So launch files can have arguments. In this case, we are not going to use, so I'm just going to leave one for example's sake, commented. Then we can have namespaces, which I'm also not going to be discussing right now. All this can go away. What is important right now is this part about the node name. So we are going to launch a node called, let's call it Earth. Then the node Earth is responsible for publishing the transformation between the Sun and the Earth. So the package is going to be PSR 22T part 11, exercise 1, and the type. So the name of the script is called circularframe.py, right? Now, we have to define here additional parameters. So I'm just going to open up this. And so we have the remap, which we can search. I don't know how to do it. I never know. Where is it, remap? We had remap. Shift F, remap. No. Strange. Param. Eu acho que ele está à procura não no sítio, em todos. Yeah, faço to include. Estranho. A minha busca não está a funcionar bem. Okay, no worries. We can search for ROS launch remap. Okay, this is it. So we can put it here. We can set here the parent. So we are going to remap the parent to the Sun and the child to Earth. And let's see if this works for start, and then we come back and fill it. Okay, so if we do a ROS launch of our package, PSR 22T part 11, exercise 1, bring up.launch. Now it doesn't work because now the parent is the Sun. So let's just say that we have here the Sun, and we can see the Earth rotating about the Sun. So that makes sense, right? Of course, now that we would have to change the velocity of the Earth, and that's a parameter. So I have to check how we can do the parameter. So ROS launch param. Okay, copy, paste, paste. We have one for the radius and another for the velocity. Radius. Let's see if the radius works for now. So the radius is of type double and the value will be 10. Let's see if when I run this, the Earth goes away, further away. Okay, so the radius worked because now the radius is 10. Great. Now we can replicate for the speed. Speed, it's double and it was 0.1. Let's say it's 0.2. Okay. Okay, so now it looks like we have all we need for each planet. We just have to go into the table, this table, and fill in whatever is needed. Okay, so if we do this, so here we have the Earth, right? Now let's replicate for the Mercury. That's the first one. So Mercury. So for Mercury, we have the diameter, density, gravity. Where is the distance from Sun? So 0.387. Distance from Sun. So that's going to be the radius. 0.387. Then the speed, where is the speed? Orbital period, orbital velocity. I think this is it, right? 1.59. 1.59. There is a problem with the scales, which I give some tips here. So multiply all speeds by 0.01 and by 10. Okay, so that's in the case of the moon. So let's just say this by 0.01. That means it's 0.0159, right? Okay, that's for Mercury. Let's do the next one, Venus. Well, thank God you are so Mercury. You are watching what I do. Mercury. And ok, era para ver se vocês estavam atentos. Venus. Okay, so for Venus we have a distance from Sun of 0.723. 723, and the speed is 1.18. That means it's 1.118. Yeah, I think that's it. Let's see if it. Let's do the Earth, and then we. Earth. Okay, so in the case of Earth, that's okay already. The radius of Earth is 1, and the speed. No, the speed is 1, and the distance to Sun. Yeah, it's always scaled around the Earth, so it's okay. 0.01 in the case of the speed. Yeah. Let's see if this works, and then we come back. Contain multiple nodes named Earth. Yeah. So this is Mercury. This is Venus. This is Venus as well. Okay. So we can change the scale of the TFs. Marker scale 1. We can zoom in. And here you have the Earth, Venus, and Mercury rotating about the Sun. And remember, this is distributed because if you take a look at the computation graph right now, we have 3 nodes. Each of the nodes is publishing a specific transformation, and all these transformations are going inside RVs, which is then using them all to draw what we are seeing, the animation that we are seeing, okay? So this is distributed. Now, what can we do? Let's just do the moon, because that's the special case. So for the moon, I want to do the moon because it's a special case. This is going to be moon. The parent is Earth, right? That's the why it's special, okay? And now, where is the moon? Orbital velocity, 0.003. Wait. But we need a couple of zeros more, apparently. And then the distance from Sun is this one, but we need to multiply by 10. So let's take away one of these. Okay. Okay, you can see there the moon close to the Earth. It's rotating, but not fast enough, okay? So let's make the speed of the moon faster, just so we can see what's happening. I don't see it rotating. Ah, it is, yeah. Still slow. Okay. Now I will see it. Now it's rotating, okay? Okay, so Why was this important? Because robotic systems often have multiple reference frames, sometimes over 100, and the transformation between the topology of the system is not is complex many times. So for example, think of a human. A human will have a shoulder connected to an elbow, connected to a wrist, and you have to make all this topology of connections in the proper order, and ROS can manage all this. I've shown you, so ROS, apart from this, we can also see something very interesting, which is the transformation tree. So take this one away, plugins, visualization, TF3. What, no TF3? That's strange. Let's see if it works now. Okay, I don't want this, I want the TF3. TF3. That's strange. Okay, not collaborating, ROS run, TF. View. So view frames is a script which will listen for the transformations for 5 seconds and then produce a PDF. Ah, great. Can it use a string pattern or? That's strange. Well, I don't know what's happening. This is a problem with my ROS right now. I don't know why, but what I was expecting to show you was this. This one here. So ROS can show from the ecosystem that is running, which are the coordinate systems in the system. Those are the names inside the ellipses, and which are the transformations between them. What's the topology in the system of transformations, okay? So in this case, you can see that we have the sun being the parent of Earth, Mercury, Mars, and Venus. And then we will have the moon being the parent of, the moon being the child of the Earth. So Earth being the parent of the moon, okay? And this was very easy to do using this circular frame.py, okay?
Those can never be some parents.
This is, well, when you say a node, what do you mean? You mean a reference frame? You mean a coordinate frame? Because a node is a ROS node, and that's you're talking about this in this context. So in this context, a node in this graph is a coordinate frame. So what you are really asking is if a coordinate frame can be a parent of itself. That doesn't make sense. To do a rotation like this, okay, we can do it. So that is this part here. So that rotation about itself is here. So let's make all planets rotate about themselves by theta. Or if you want, how do we call? Esqueci-me do nome para a rotação sobre si própria. Agora esqueci-me. Which one? Itself? Sim, mas não é rotation speed. Internal speed. É que não faço a mesma ideia, esqueci-me do nome. Não, eu estou a falar da órbita. A Terra tem uma rotação. Okay? Ah, right. Very nice. You don't know, but you know where to find it, right? Escape velocity, length of distance from sun, orbital period, orbital velocity. I think it's orbital velocity, no? Pois, é capaz de ser. Revolution. Gosto. Vamos fazer uma revolution. Evolution. Okay, so let's say that we have here a revolution, which is a revolution speed, in fact, and we can use it to change the value of an alpha. YY, and so let's do here the alpha. This is the revolution. And here is the alpha as well. Okay, and finally here, oops, also. Okay, so I did the same, but what I'm changing now is this. This is all done in the z equals 0 plane. If you take a look at RVs, you will notice that's the case. Okay, so this is z equals 0 plane. And, but the ROS operates with transformations in 3D always, but they are right now without the z component. Which means that if you take a look at these three angles that we have here, these are the Euler angles. So that's the rotation about the x, that's 0, the rotation about the y, that's 0, and the rotation about the z. So what we are rotating is when we change the z, where the alpha is the pose in the x or y plane. Let's see what happens. So now I think all of them will be rotating about themselves. Okay? Makes sense? Of course, they are all rotating about themselves with the same speed. Now we would have to go and check and put different speeds for each. Okay, so where do we go from here? Let's just do this one here. And then we leave the URDF for the practical class. So this is all very nice and very nice animations, but what really we want to know is at a particular moment in time, let's say we have a spaceship and we are moving from the moon to Venus. And when we move from the moon to Venus, we want to make sure that we depart whenever the moon is closer to Venus. So we want to measure the distance between the moon and Venus, okay? So we want to listen to a transformation. So let's say here that I'm going to create so I'm going to copy paste this one. I'm going to do the listen moon to Venus. I'm going to call him this. And this moon to Venus will have to periodically compute the distance between the moon and Venus. How would you go about doing this if you didn't use ROS? You would have to collect the distance between the Earth and the moon, then the distance between the sun and the Earth, and then the distance between the Venus and the sun, all taken at the same time instant, and then compile them together, typically by multiplying the transformations. So this is no big deal. You can do it by hand, but ROS solves this problem automatically. You just have to say, oh, give me the transformation between the moon and the Earth and Venus at a particular time frame. You do that. ROS by TF listener. Okay. So this is an example. Diga? As TFs são uns tópicos especiais, depois eu posso falar um bocadinho mais disso, são tópicos especiais porque tem alguma coisa em cima disso, porque eles fazem um buffer local. Mas sim, mas é tão simples quanto isto, você já vai ver. Não, espera lá. Vamos passar com isto. Okay, so we initialize the listener Venus to moon to Venus. So we initialize a listener. That's just an object from ROS. Then we are going to wait for a service. This is not important. Not important. What's important is this. We are going to do a for loop, and let's say at every second, we are going to try to get the transformation between the moon and Venus. And then we have to say at which particular time. This Ross pi dot time 0, that means at the latest available time, the earliest available time. And then if we have an exception, we just say print.
Earliest, like the latest one, or
Latest, earliest, yeah, earliest, mais recente. That, is it earliest or latest? Latest. Yeah, right. Could not get the transformation.
if you use cross profile language now, it would say we are trying to access the past, for example.
Oh, that's wait a little bit more, I will tell you, but it's an explanation of 10 minutes and I don't have 10 minutes now. So let me finish this one and then I will tell you in the practical class, okay? So this transformation will be a transformation which will contain a translation, it's there. So I can just print the translation and say distance. First, let's print the translation. Trans, okay? Okay, so if we run our new node, ROS run PSR 22T part 11 Moon to Venus, will not get the transformation. Now it's getting the transformation. So you can see here that this is a list with 3 values. That's the X, Y, and Z coordinates or distance between the Moon and Venus. So if you want the distance, you just have to do distance equals trans 0 to the power 2, trans 1, 2. And because we are talking about the Z plane, the X or Y plane, Z is always 0, so I don't have to add it. And this will be math.sqrt. Okay, so this is my distance. And now I can sqrt, not srqt, sqrt. And now print distance from Moon to Venus is distance. Now you could do, for example, a threshold. When it's below something, the spaceship can go. Let's see. Okay, so the distance between let's try to take a look. So the Moon is there and Venus is there. They are more or less closer because the Earth and Venus are moving more or less at the same speed. So let me scramble things a bit by doing the following. Let's say Venus moves twice the speed it's moving, or 5 times the speed it's moving, okay? Just to make so that the distance should change. Okay, so you can see here Venus moving. The distance is going further and further away. And then when Venus goes nearby the Earth and the Moon, the distance should be small. Okay? So now it's 0.7, 0.4, 0.3 was the closest one. Okay? Okay, TFs are a very, very powerful tool. I've done many things with TFs in ROS. It's really helpful. And I think one of the most successful packages, but I say this about almost all of the packages, so don't trust me. And the question from Bruno, why can't I get the distance if I say ROS TF now? Because what ROS is doing is it will get a particular transformation at a moment in time. What happens if you ask for the transformation 10 seconds from now? So if I tell you, where is the Moon going to be from Venus? What's the distance between the Moon and Venus in 10 seconds? You know, because you know the orbits and so on, so you can compute it, but ROS doesn't know because it's just observing transformations. So it doesn't know how to extrapolate it onto the future. When you say ROS time now here, so if here you say ROS time dot now, what you are going to do is to ask at this very instant, and it may be possible that at this very instance we don't get the transformation. So That's, yeah, I told you I need 10 minutes, not 5 seconds to explain this. So I can try to elaborate more in the practical class, okay? Bruno, we can speak better later on. Let me just use these last 4 minutes for something else, which is to present you the beginning of the practical assignment. So we are going to do a new practical assignment this year. It's not the same as last year for several reasons. The biggest one is that I wanted to change and to do something more interesting. I really like the one from last year, but I wanted to change. And we are going to do something different. So last year was a competition between groups. This year is not a competition, but I call it Robotler. Robotler is, or stands for, the robotic butler. You know what a butler is? Mordomo, no? Okay, so let me show you. So Robotler. Ross launch, butler. Okay, so if we launch Gazebo, suppose that you have a robot in your house, okay? I will tell you how to use a robot, how to configure one, and we are going to use a simulator. So this Gazebo is a simulator, and we have a house, okay? So this is an apartment, a 3-bedroom apartment, and we have a robot that we want to, I never know how to do this without the mouse. Okay. Okay, I don't know how, yeah, now yes. Okay, so you can see here some toilets, some restrooms, an office, the kids' bedroom, the bedroom, then a corridor, a balcony, a kitchen, and some living room and dining room. So that's your apartment, and your robot should move around this apartment. So you are going to build a robot. I give you this scenario, and you are going to be the programmer of this robot, this service robot. And what are we aiming to do with the robot? We are aiming to solve several problems. I've thought about 2 or 3 already, but then I will try to think of more problems. And if you have suggestions, tell me. So I will try to do an assignment where you have to fulfill missions. So the robot can be standing, and then I tell him, can you please? So for example, look, I can do something like this. I was testing this yesterday. Ross, run. What's the name? Robotler. Description, spawn object. So I'm going to spawn an object. So you can see I just spawned a violet sphere on top of the cabinet. So suppose that the robot was in the living room, and now I would ask the robot, search for my violet sphere. So the robot would have to wander around the house, explore the house, searching for this particular object. Something else we could do is do something like that. I can do, for example, where is it? So I can put a green book somewhere, and I say, search for the green book. And the robot would have to go around searching for it. I can also say something like, where is mom? And the robot will have to search for where mom is and then reply, she's in the office, okay? So it's like a butler that you can ask for to do several stuff. Well, it's typically passive stuff because I don't want you to die, because if you try to do manipulation, then you will die. But I can do something like, please push the chair. The robot can try to push the chair by just moving forward towards it and accelerating it. So you will have many missions, and you will have to implement the interface for these missions and how to solve them, okay? I will give you the gazebo. So I was doing this last night. This apartment I give to you, and this is the starting point. And then we will add objects that you don't know where they are, and you have to search for them and tell where they are. So this is going to be the assignment. Vision robotics, you have to navigate using SLAM. Then you have to use vision for detecting the obstacles. You have to use LiDAR for measuring sizes, and so on and so forth, okay? Yeah, I think it's going to be difficult. That's why I'm so happy with the idea. Sim, conheço. É parecido. Já, acho que nunca participei, mas estive quase para participar. Yeah, so you can try. I told you in the beginning of this year that I told you, but I don't remember the answer. Is it that I randomize the groups again, or do you want to choose the choosing this third assignment? Okay, so start sending me emails telling me our group for this third assignment is this and this person. Okay, that's it. Okay, by next week I hope to have at least a draft of the last assignment so that you can start working already. It's not going to be finished, but it's going to be something that you can start working on already.
Next, not this time. Next, yeah, next class, the next class would be already trying to get started.
Next is next week, right?
Yes.
No, we still have to teach. I still have to teach you a lot of stuff. Everything that I teach you is useful for the assignment, but it's not going to be, do the assignment, I have nothing to teach you. I still need,
There's always stuff.
yeah. For example, Slum, I didn't teach you how to do Slum, and that's important for navigation. But don't count on me teaching everything you need. There will be some stuff that you need to search on your own because it's impossible.
Google those things.
Exactly. Google before thinking. Vamos lá então, malta.